and we just jump in here. And I suppose, just the purpose of this is just to, I'm sure Eugene will have something to say too, but it's just to raise some question that bring out the commonalities and differences between all the different talks that we heard about the history and philosophy of equilibrium reasoning. And I mean, like, just to maybe to bring stuff to everyone's attention, we've heard a lot of stuff, right? We started with Archimedes and the Greek philosophers and the Greek poets. And we learned a lot about Newtonian and classical mechanics more broadly, with equilibrium of forces and its different guises. And we've heard about thermodynamics, thermodynamics, classical thermodynamics, statistical thermodynamics, quantum statistical thermodynamics, and we've heard about application of equilibrium reasoning in general relativity, in economics, and eventually in biology. I hope I didn't forget anything. No. Okay, so a lot of ground was covered. I think, like, philosophically, we covered a lot of questions of conceptual change and how different concepts of equilibrium relate to each other. We talked about equilibrium as an idealization in frequent talks, equilibrium as an explanation. And I think there's many natural questions that arise. And there's, I guess, common historical trajectories, right? Trajectories towards generalization abstraction, like the one Michael has described, but also many cases where, like, equilibrium concepts were developed in response to specific empirical challenges or theoretical challenges that people face, say, in economics or in Newtonian mechanics. So I think there's a lot of natural questions we could ask that connect and transcend these talks, given that they have those common philosophical, historical, philosophical and historical dimensions. So the idea is to open up the space to discuss some of these. If you have any thoughts, go. I have lots of thoughts, but if you have any thoughts, now's the floor to ask other authors and to try to, like, connect the ideas that we had in one way or the other, whether philosophical, historical, or otherwise. Yeah. So, who wants to go ahead? Who wants to open the discussion? Wayne.
Everyone's afraid to break the ice because they don't have anything profound to say. So I'm going to say something that is obviously not profound to make everyone feel better. I really like this has been really valuable experience for me, particularly the historical talks having to do with Archimedes and statics, and then the development of mechanics, because it brought home for me what a big that I in ways that I hadn't really thought of before. What a big change it was in the concept of equilibrium that was brought about by the kinetic theory of heat. And like when Archimedes and everyone else was doing statics, they were thinking, okay, this is a stable situation in which nothing is moving. And even in the early days of molecular theory, Laplace, for example, thought the gases were composed of molecules, but he took literally the macroscopic stillness of the gas, and he thought the molecules were just held in, that were actually motionless in a state of equilibrium, that they were, they had a natural attraction, and then caloric was pushing them apart. And it really is like, and even late in the 19th century, when Poincaré is there's an incident where Poincaré is trying to develop a mechanical analog of the actually no, this was Poincaré's criticism of someone else who I don't remember. But attempts to develop mechanical analogs of the of thermodynamics. People were thinking, oh, equilibrium has to be correspond to a situation where nothing's moving even at the microscopic level, and the idea that in the stillest lake has molecules that are moving around at many times the speed of sound and colliding with each other billions of times per second, I think is a really radical shift. And it's what causes all the interesting issues about trying to explain equilibration in physical mechanics.
Yeah, so just to follow what Wayne just said, I think, like, under the title of the workshop, there's another cool word that we should emphasize more. Maybe that's finding balance, like over equilibrium. Like as Wayne just said, thinking about equilibrium and thinking about how to apply equilibrium in our work to quantum mechanics we learn a lot about the time scales, we learn a lot about the perspectives from which you look at the system, be really telling you more than like the static thinking or stationary thinking. So the word like balance is really play, the roles of work here. So I would like to invite everyone to think about like apart from the terminological issue about like, because like, sorry, to be bad people here, some people like of us use the equilibrium to mean idealized. Some people use it to mean stable, stationary, but like it's better to have some more strict requirement for the notion of equilibrium. So I think like finding balance might be a good way toward maybe we can have a better notion of equilibrium to include more case of studies.
Maybe I can add a quick comment on what Wayne said about equilibrium. One thing that I think really distinguishes between other forms of purely mechanical balance and the thermal case is just that a thermal balance is a property also of the coarse graining at which you look at the system. So it's not purely a property that you can derive from observing a system, without any theoretical apparatus, for instance. And it could be the case that a system that looks at equilibrium, at one level of observation is not an equilibrium at another level of observation. And for me, that's a very interesting property of thermal equilibrium that is probably not shared by some other forms of equilibrium. It could be a purely mechanical form of balance. And the second thing that I find interesting about thermal balance is that what I mentioned in the talk as well, which is the structure of thermal balance itself is very detailed in a certain sense. It has a very specific structure. And it could be that there are other states that also have a very intricate balance. So it's not just balanced at some level, because the motion is microscopically reversible. It is in detailed balance at certain nodes. It's also that despite these conditions holding, which is reversibility and detailed balance, you have to have this additional property of a certain structure of the detailed balance that will give you a thermal balance. I think that's what for me these two things distinguish a thermal sense of equilibrium from a purely mechanical form of equilibrium. Yeah, thanks.
Oh, I have the other mic here. Okay. I guess I'm just going to be selfish. I'm very curious about, I don't have anything to add to the considerations about the strict definition and distinction between the thermal and the mechanical equilibrium. But I've grown convinced that this is actually quite an important issue to pull them apart, partly through this workshop. But I'm very curious. So I guess like a major motivation for Eugene and me, but which is reflected in the like kind of work that, as you saw, both of us do, of course, which is not the work that everyone does. You have different interests and like goals, and that's how it's supposed to be. And it connects, I think, to Dennis's and August's talks. But we're really interested in zooming in on the commonalities, right? And commonalities at the level of methodology, right? So wouldn't it be interesting if in all those different definitions that we find of equilibrium throughout the history of physics and perhaps in other sciences, the use of equilibrium reasoning is somewhat similar, right? Like we're interested in some form of counterfactual reasoning. We have some crude ideas, maybe of stationarity, with which we start, that then like in the conceptual development we refine, like to what Eugene said. But it just proves to be such a general and actually quite potent way of explaining the natural world, right? To reason from equilibrium to disequilibrium, and thereby revealing counterfactual dependencies. And you can make sense of that by further specifying it in the different cases. Like, what exactly do we mean by balance? What is the theory of the balance that we use, et cetera, et cetera. But it seems to be, to me anyway, somewhat structurally analogous in all of these cases, right? And I wonder whether that claim makes sense to everyone in the room, and if so, what are the implications, and is there a risk of overgeneralizing, right? And how do we deal with that? Please enlighten me.
Just a very small thing. I wonder if it's actually not a feature of the world that these are the kinds of, but it's a feature of our models, as in those are the simplest models, or they reveal some kinds of ideas. So I would just add that maybe that's what we're after, actually.
Yeah, I want to tie into what Aditya said and also tie into Dennis and Augustus' talk, because as you pointed out, the concept of equilibrium in statistical mechanics and is depends on the coarse graining. Like there's lots and lots of change going on at the micro level, but certain macro properties are steady. And the idea that that could be possible actually came from studying human populations. And things like in human and animal populations, sex ratios can be relatively constant in a sufficiently long population, even though what's happening is individual organisms of both sexes are dying and being born, and at a micro level, the actual ratio is fluctuating a bit, but over at a coarse grained level, it's almost exactly 50-50 steady in time. And I think that, that sort of reasoning, the idea that there can be certain macro variables that are constant while they're as a result of lots and lots of rapid changes, I think is an important idea that isn't in a lot of sciences. In fact, well, people in the 19th century started distinguishing between dynamical regularities and statistical regularities, and Maxwell claimed, it took me a while to realize this is actually correct, all the regularities we perceive are statistical regularities. They are aggregates of lots and lots of individual unpredictable things.
Oh yeah, I guess I would like to add to Wayne's discussion too. I guess you're saying, I guess some people thought that I guess you're saying that there's like a big gap, or like not gap, but like leap from this mechanical to the thermodynamic kind of equilibrium. I was wondering whether like there's some kind of intermediate zone where, say, when we got to like the principle of virtual work and we allow for dynamical equilibrium, it seems like in that case, like things are change. There is like change, but there's a sense in which something is not changing, but that is no longer the system's literal intrinsic state, but something more general, like some kind of law-like thing, and that kind of connects to, well, the Lagrangian, which is like the thing that becomes that is stationary is no longer even like a state of the system. It's like some kind of function, some kind of law that is optimized or unchanging not even like a physical change, right? It's like in trajectory space, and that's kind of a I'm not sure. Yeah, it's like there are all these connections there that I'm trying to figure out myself. But maybe it's like there's this intermediate zone between the literal unchanging and the literal, like the thermodynamic picture, in which we're already moving towards it even in the mechanical regime. So I was wondering, maybe like Michael or Miguel has more to say about that. But once you got to that level, then already there's a sense in which there's this distinction. It's not within the same system, but there's like a law-like level where something is unchanging, some function, yet the system could be changing, could be moving. There could be a kinetic energy, could be potential energy. But yeah, so I don't know if that's that makes sense, but trying to connect those things together. Yeah.
I'll keep thinking about this. I struggled a lot in trying to frame my own talk just because of as I started to think about these materials, finding how, I don't want to speak out of turn, but like relatively primitive the notion of, or how limited the notion of equilibrium was in this period. And so that's why I kind of took it in the direction I did, because it just, in all of the examples I could think of, equilibrium really was restricted to this kind of balance of forces picture. But I'm going to keep chewing on your question because I can't think of anything more to say about that right now.
Yeah, this is a small point, but technically it wasn't just a balance of forces, right? Like you can think about the canceling of work, no work being done. Right? And like Wayne was just stressing, it's a very old idea. It is certainly stated explicitly, not under the name of work, in Galileo, when he's thinking about not just the balance, but motion under constant gravity, right? Which the balance helps you to model. And under those kinematic conditions, he gets the idea of, oh, like he wants to prove something about path independence, and naturally arrives at a concept of work, which happens when all the, like all the, you need to, the same amount of work is invested along all those different paths, gets them the path independent. So, and then I guess like you can see that what happens is that while the picture of like a work, like a mechanics primarily based on actual and virtual work, is in some sense equivalent to the force picture, there's a reason for why there is the push towards generality, right? That in some sense you in your talk traced. And in some sense even that came up in my talk as the systems to which we apply the like cruder notions of equilibrium just get increasingly complicated, and it becomes easier to reason about them and their perturbations in terms of work-based or potential-based concepts rather than forces, right? So I think that's the way in which the concept is already changing, but I guess it's still a very far cry from like the thermodynamic one, which is evidenced by the fact that Laplace at the same time that he thinks about thermal physics and that he develops these new formulations of mechanics is still endorsing the picture of like, kinetic theory that Wayne described.
Thanks, Miguel. This is a sort of a, continuing that thought ahead. And what I learned from one of the talks, Miguel's talk in particular on this topic was, how Newton came up with an abstract framework of forces, sort of doing away with this particular forms of reasoning, using levers, mechanical systems, and so forth. And, a force-based reasoning was very ingenious at that point of time. And on a similar line, analogous line, the form of reasoning based on equilibrium, I think, is also ingenious in some sense that you don't need to have particular systems of different kinds, a biological system, a gas-based system, and you can learn a lot about a system, using its sort of equilibrium in some sense. So it's a very rough analogy, but I think it's very, this form of reasoning itself, I think, is very, very helpful, which sort of does away, which does away with the particulars of a system. So it deoperationalizes in some sense, sort of, does away with the particulars to go to a more abstract way of modeling a system or looking at a system.
Yeah, and there's at least like two commonalities. Like as Eugene, we've been first thinking for a while about the commonality is like about the counterfactual reasoning that equilibrium as the equilibrium states immediately carry with them a theory of properties that could explain disequilibrium. And this is something interesting to figure out in science. But there's the second thing that a lot of you identify as peculiar about equilibrium reasoning, which is it naturally itself to coarse graining, right? Which also comes up in Dennis's account of equilibrium reasoning. So there are at least two facets that come together generically.
Maybe a quick comment if somebody has no comment on this. And I think one motivation is that this kind of reasoning, which relies on a system's equilibrium, it does away to some degree with its dynamics, which is not to say that we don't need systems dynamics to explain what's happening. It is to say that 2 points. So one point is that when we abstract away from dynamics, we start seeing what could not be relevant to the explanation we want to get at. So certain systemic properties can be explained without necessarily referring to its dynamics in some form. And the other way, which I think maybe my head is a bit scrambled at this point. Yeah, the other way is just the tractability of an explanation as such. We find very detailed causal explanations that track every part of system history very hard to track. And using something like equilibrium does away with this tractability problem in some sense. So the task of explanation becomes significantly simpler compared to some of the earlier cases. So the 2 points sort of in a nutshell, one point is that when we abstract away and go to the form of equilibrium reasoning, we learn what is not important in our explanation, what's not a fact that plays an important role. And second, it gives us some tractability in our explanations as such. Yeah, thanks.
I guess also like a maybe broad, bigger picture question. I'm wondering what exactly is the shape or the form of equilibrium explanation, right? Because the ones that are often discussed in biology by, say, Elliot Sober and the rest is there's a kind of there is a kind of teleological flavor to it, where it's like, well, the system approaches the equilibrium state, but I feel like it relies on an analogy to the statistical mechanical or thermodynamic kind of equilibration picture. Like, I guess I was thinking like maybe pre-thermodynamics, like the kind of equilibrium explanation we had in mind, but more like, well, you began in equilibrium and then you consider perturbations and then you study that. But that's a different kind of use of equilibrium in explaining something, right? That's more like Miguel's talk, and also maybe Sarah's talk to some extent, like, like the balance, studying balance, yeah, and Helen's talk and so on. Yeah. Those are like different kinds of user equilibrium. You start with equilibrium thing and then you go out of it, as opposed to equilibrium is the thing that you're trying to get to, and you know how to get there. You're using that back to explain something. Yeah, so I'm wondering what exactly is the form, or maybe these are just two different kinds of they probably are just two different kinds of equilibrium explanations. I was wondering whether we have been focusing too much on one and not the other. Yeah.
Yeah, I wonder whether whether there are different types of equilibrium. There might still be. I think it's very probable the different types of equilibrium explanation, but perhaps the kind of thing that comes up in the applications of mechanical equilibrium and GR or in like the stuff I talked about. Like we're looking for tractability, and tractability for then studying, I don't know, like a large class of different possible solutions, exact solutions that each is an equilibrium solution in some way, or perhaps the first ones that we get are equilibrium solutions, or we're interested in the perturbations of these, etc. So it's like a means to an end, right? But the part that the part that you describe as actually we're interested in the perturbations and we use it as an idealization might not be in the explanatory part of that story, right? We first, because solutions are also some kind of explanations, right? So you could still say there's an initial equilibrium explanation of sorts, even though it might not be teleological in the way it is in thermodynamics and biology. And then further, we use models that also act as equilibrium explanations to then reveal further details about the systems doing some kind of counterfactual reasoning, right? So those two must not conflict always, I think is what I'm thinking. Yeah. Okay, so August has a point, and then Yishin, and then
yeah, on this point, some of you may know that there's this very long history of sort of thinking of optimality and equilibrium explanations as kinds of teleological explanations, or trying to claim that all a teleological explanation is an equilibrium explanation. And this goes way back. I mean, of course, it's anachronistic at a certain point, but you might think that, Aristotle's explanations of motion that have a strongly teleological character, and his explanations of his genuine teleological explanations of in biology, have this analogous structure. You have sort of Maupertuis and Leibniz, of course, arguing about teleology and optimality. Of course, there's a theological dimension here, and I'm not an expert, but and then all the way into the 20th century, in debates over the place of teleology in biology, there's people saying, oh, well, really all we mean here is a sort of equilibrium explanation. There's nothing spooky going on. And that's really interesting. And I think what I haven't seen, and I think maybe what we're trying to do is to make really explicit, like, what exactly is the analogy here? And the idea is that they're both consequence explanations. And maybe that's just too obvious, and which is why people haven't mentioned. But I think that's really what's at issue, and hopefully like clarifying, as Miguel was saying, like the ways that equilibrium explanations explain, and maybe there's many ways that they explain. And this is something we've been struggling with. Is sort of an attempt to make all of that clear. And I think it's really interesting that I've spoken to a few physicists and mechanical engineers and mathematicians, and there's just really no clear answer that I've seen when you ask them, like, how exactly do equilibrium explanations work, and like, is there one or like many answers to that? You don't just get like one clear answer. So clearly there's no clear consensus, and even the idea that the equilibrium point might explain in certain circumstances seems quite controversial and like unclear to a lot of people. And I don't quite know what to make of that, but I think it's sort of revealing of something, and some things that need some sort of clarification. And so, think it's really interesting for that reason.
Yeah, I think I've had something to add to the topic of explanation. So I do think, in my experience, that equilibrium reasoning, or like the model of different sorts of equilibrium models, stationary ones, idealized ones, the first level is you will be wondering why it's so universal that you can find in different sciences or different explanation that you can use such a simple model to explain different phenomena. But at this level, you might think, well, for example, in the like debate of minimal model explanation, why you can use such a universal model to explain so many different like microscopic complicated systems. But I think there's a very good code that I got from, or maybe it's not code, but it's thought from Udur's paper. He discussed like causal and non-causal explanations in 2018, in which he said, well, yes, for the problem about why minimal model can be explanatory, there could be two layers of problem. And first one is why the minimal model is apt for across different phenomena. And the second one is why the model is that model for a specific system to behave in this way, right? So the first layer could be different kinds of non-causal explanation or like mathematical explanation or equilibrium explanation, but at second layer, it pushes us to understand the dynamics and the causal details under which you can perturb. You understand the stabilities. You understand, the deeper balancing layer in which you have causal information that tells us, for example, why black hole model is so simple, because you can have like physical dynamics that perturbing around it, and so it goes back to it because of GR, blah blah blah. So that's like you talking about equilibrium models or minimal model or idealized models, stationary models, actually could give us like different layers, different senses of how to understand types of explanation in science. So that's my general take.
I feel like this is related to what this thread that's been going on right now. I feel like you were distinguishing at least two different things that the equilibrium tool is doing. And so one question is something about how should we characterize the way a system behaves over time? How do we do it? We characterize it as moving from equilibrium state to equilibrium state. That's one way you can use equilibrium, which is to articulate your problem in the first place, the system of interest. The second thing that you might be asking is, why do a whole bunch of different initial conditions end up in this terminal condition, which is an equilibrium state? And that seems to me a different question. They're not incompatible, but that just seems to me they're playing different roles.
Yeah, I was thinking
The mic just disconnected, I think.
Should I use this? Now are you hearing me? Great.
Yeah, loud and clear.
You guys don't need right. So I'm surrounded by people who keep using the phrase equilibrium explanation, and I feel like I'm the only person in the room who doesn't know what that means. So what is an equal? So, like in thermodynamics, someone might ask, like, why are these parameters rated in this way? And you could say, well, because that's the equilibrium state. But as Gen just pointed out, you can it's still a question like, well, why do things head towards equilibrium? And that was what my talk was all about. There's all this literature, and I think the answer is not because that's the consequence. It's not Aristotelian. They have the gases have the goal of reaching equilibrium. So what do we mean when we say an equilibrium explanation? I honestly don't know.
Well, I think I'll just say that, no, I think we're all to a certain extent puzzled about it. But I think we all think there's an answer to be had, or maybe multiple answers, right?
I'm happy with multiple answers.
Okay. Yeah. So I don't know either. I like the Walsh Nahas account, but I don't think that like to connect with what Jen was saying, I don't think when at least I didn't take myself when I was talking about equilibrium reasoning or idealization, I was talking about explanation, right? because it's not like the assumption of an equilibrium state that explains why the Earth has the shape that it does, right? It's rather that this is an assumption that you make to apply a theory that is Newtonian theory of gravitation that explains why it, right? So it's like the use of an idealization that involves equilibrium in perhaps an explanation, but primarily in prediction, right? And I think that applies to, I would have thought, how it's applied in economics even too, right? Even though I guess there's both. There's many things. I don't know, like who wants to, yeah.
If it makes you feel any better, I actually can do the following, which is I don't think I understand what equilibrium is. Never mind the explanation part. And here's one thing that falls apart in the economics case that I got really stuck on while I was writing this paper, which is optimization doesn't automatically come along with equilibrium in economics. Like in the very first case where I was saying the market clears, I didn't give you any story about optimization until I added this extra detail about efficiency. But you can tell that story about market clearing without the efficiency argument. So it often seems to me that equilibrium comes along with this package of things that it doesn't a priori come along with. And in any case, I'm to this day still puzzled as to what the equilibrium concept is. So
Oh, thanks. Yeah, Wayne, I'm with you. But there could be many senses in which one might offer an equilibrium explanation. And I think what August and I were trying to do is that like, there's, a specific sense in which on certain occasions you can use the fact that the consequence realizes an equilibrium to explain the trajectory. But there may be many other forms of explanation that count under the umbrella of equilibrium explanations. What's the structure of the system such that it should tend towards equilibrium? Those kinds of things. So I don't think that we have to take it that there's any one thing that an equilibrium explanation is. But it might be nice if we could articulate the various senses in which there are equilibrium explanations. But I wanted to get back to it. Oh, sorry.
No, go ahead. I'll go after you.
Well, I'm just going to change the subject a little bit, but I wanted to get back to something that Miguel said, which will help me, I think, will help us with the question Wayne had about teleological explanations. So Miguel said something to the effect that, look, we can use equilibrium to kind of give us some understanding of disequilibrium states, right? When a system is in disequilibrium and our expectation is equilibrium, then we can use the expectation of equilibrium to find out something more about the system. Is that the general idea, Miguel? And I think that kind of gives us a sort of partial answer to Wayne's question about degenerate cases of teleology. So when the goal directedness fails, you can use your understanding of the dynamics of goal directedness to explain the cases in which the goal directedness, so you kind of get teleology, goal directedness, and you can understand the general relation between means and ends as a way of leveraging understanding of what goes wrong in a way that's analogous to leveraging the understanding between, say, trajectories and equilibria to leverage an understanding of what goes wrong in the disequilibrium case. Would that work?
No, you answer first, and then I don't think I have. Oh, okay.
Oh, okay. I just want to understand how you're using the phrase degenerate case, because I wanted to distinguish between goals and consequences, because I think so is a case where a goal the consequence is not the goal. Is that the degenerate case? Is that what you mean?
Yeah, look, I take goals to be the success conditions of an action, right? which is to say the
Yes,
outcome
so,
of it.
So, but the success conditions of an action aren't always the outcomes, or even often the outcomes.
Yeah.
I think as we were talking about this, it occurred to me that, we just had a World Cup, and so there's stats available of how many shots on attempts at goal were made, and stats available of how many of those were goals, and I'm guessing it's roughly 3%, right? But in each case, the goal was, of those attempts to goal, was to score a goal, and we can explain the behavior with reference to that goal, even though this is actually it's rarely we can we explain the behavior of the players by saying they're trying to score a goal. In fact, I can't imagine trying to explain the behaviors any other way, even though in the vast majority of cases that actually isn't a consequence of the behavior.
Yeah, that's a really good point. So I guess the idea here is that, like in the equilibrium case, if it weren't the case that in the successful circumstances we could explain actions by citing their goals, we wouldn't have any way of explaining what goes wrong when things go wrong. And then in the equilibrium case, and certainly in biology, it's extremely rare that biological populations are at the equilibrium case, right? So it's about as rare as successfully taking a shot on goal. Right? Nevertheless, you can use the equilibrium expectation and the form of an equilibrium explanation to kind of enhance your understanding of why this particular system has these particular characters, which is to say they're disequilibrium, right? And I think the same is going on in the case of failed actions, as it were. We use the form of a teleological explanation to enhance our understanding of action in cases where the goal isn't achieved. But were it not the case that you could, in the successful cases, appeal to goals to explain their actions, you wouldn't have that kind of epistemic strategy available to you. That's the general thought.
That's very helpful. Thank you.
Yeah, just on Wayne question, one thing that I was thinking about is that in general, like in physics, when it comes to mechanical equilibrium, in many cases, there's not really anything special per se about equilibrium, right? I mean, we always have we can always look for a higher order evidence of a different type of equilibrium of the system. So perhaps like the special feature of many equilibria that are studied in physics is just that they are simple to treat. They're like the simplest situation that we can face to begin approaching a problem. And so we look to the one that minimizes the variability of certain parameters, but perhaps there is nothing special per se about this equilibria conditions.
Guess it's time. Yeah. Well, well, I guess with that oh, Diana wants to. Oh yeah. Sorry, I didn't see the hand. Yeah, no,
absolutely.
A point that was not raised in this workshop, I think, but that is sort of in the background of the stuff that I've been doing in the origin of quantization. This emphasis on the importance of thermodynamics related to Einstein's distinction between principal theories and constructive theories. I'm not sure if all of you are familiar with the distinction. So you have that principal theories, well, their foundation is secure, right? And from them, you deduce constraints that the constructive theories must satisfy. And he took his special theory of relativity and thermodynamics to be the examples of principal theories, right? And so the way that I was also interpreting the quantum revolution is precisely, well, it was realized that there was this equilibrium constraint, right? That the classical physics theories were not satisfying, so we just have to modify them to accommodate these constraints. So if you take that approach, then you can have one answer perhaps to what is an equilibrium explanation also, right? That you just demand that your constructive theories satisfy these constraints. I'm not sure.
I know we're closing in, but I do think this is a very good point. Like, it's a very interesting point. And I know that at least in the story Michael told in his talk about the development of classical mechanics. I mean, Catherine Brading and Marius Dunn, I mean, they have a slightly different understanding of what principal and constructive theories are to Einstein. But they make a very similar point that the strive towards generality in classical mechanics came from the inability to find a constructive theory about like plastic and rigid body motion and plastic solids and all that kind of stuff. So physicists essentially, or philosophers who were initially tasked with doing that metaphysically, just gave up and instead came up with the mechanics based on constraints that you articulate in a much more abstract way that give rise to least action and all these kind of principles that Michael then discussed. And I guess you could even, now that you think about it, think about the transition in mechanics from Galileo to Newtonian mechanics as somewhat analogous, right? Like, because the idea of like mechanistic causality gives you some kind of constructive theory about force, right? And Newtonian mechanics, well, maybe that doesn't work. Well, it's like not everything that's general is a principal theory. Yeah. But anyway, I'm just saying, like, there are analogies to what you describe about the way that like a notion of equilibrium that comes from a principal theory drives the development of a constructive theory, in this case quantum theory, in many other like areas in the history of mechanics, and I'm sure also other sciences, right? So I think it's a very interesting link that we should think further about, that distinction versus equilibrium reasoning and other kinds of reasoning. Yeah, that's all I had to say. I don't know if Eugene, you want to say any last words? Words of goodbye.
Yeah. Well, I feel like every good workshop ends with inability to answer the question it seeks to answer. So I think we've discovered that we have many ways to understand equilibrium, but I'm not sure we've fully pinned it down yet, and that's great because there's more work to be done. More things to think about. Yeah, we did make progress, and I feel like I learned so much from this workshop, and a lot of things I need to process and think more about, which I'm kind of scrambled at the moment. But yeah, so I guess on that note, let's thank everyone for thank yourselves, I guess, for coming here. Right.
Thanks, everyone.
Yeah.